We're going to talk about section 12.9, determinants and vectors in 3 dimensions, and learn a new multiplication of vectors called the cross product. So we know that we can write vector OP, say vector OP is given in component form as 3, 5, 6, that we can write this also. So we know this vector can be written in ijk form as 3i plus 5j plus 6k, where the I, j, and k are unit vectors in the direction of the axes, where I is 1, 0, 0, that's a unit vector in the direction of the x-axis. J is 0, 1, 0, the unit vector in the direction of the y-axis, and k is 0, 0, 1, the unit vector in the direction of the z-axis. So we're going to use this ij notation to define a new operation. So we use ijk notation to define a new vector operation, called the cross product. So it's a cross product of 2 vectors. So let's get the definition and then we'll see how it works in practice. So if v is going to be the vector, say v1, v2, v3, and w is going to be the vector w1, w2, w3, then we write this as v cross, and we use a big X like you're back in elementary school using a multiplication symbol X. Notice how that's very different and cannot be confused with the dot product symbol, which is just that, looks like a multiplication dot. And we read this as v cross w. So v cross w is by definition going to be, it's going to be a 3 by 3 determinant. So we're going to go I, j, k across the front row, the top row, and then the order matters here. Since v came first, it's going to be v1, v2, v3 as the second row, and w1, w2, w3 as the third row. And so this gives a vector. So the answer to this is a new vector with some pretty remarkable properties that we're going to investigate. But let's figure out how to do it first. So let's say that v is going to be 2, 3, 4, 2, 3, 4, and we'll say w is going to be 1, 0, 5, 1, 0, 5. Then we're going to say that v cross w is going to be, and we're going to go I, j, k, and then 2, 3, 4, and 1, 0, 5. Now, the way to do this is not by recopying those first 2 columns, but we're going to do expansion by minors. So we will use expansion by minors and always along the top row. So expansion by minors along the top row. So when we do that, we're going to get I times, and in its minor, remember, we're going to cross out the row and column that it's in. That's going to leave us with 3, 4, 0, 5. 3, 4, 0, 5. Then remember, we're doing a sign along that top row, so it goes plus, minus, plus. So it's always going to be a minus j, and then times j's minor, and if you cross out the row and column that j is in, we'll be left with 2, 4, 1, 5. 2, 4, 1, 5. And then it's going to be plus k times its minor, and we cross out its row and column and get 2, 3, 1, 0. So then evaluating this, we're going to go, I guess I'll come this way. So we're going to go down minus up. So that's going to be 15 minus 0 times I. And then we're going to get 10 minus 4. So that's going to be a minus. And then a 10 minus 4j. And then we're going to get 0 minus 3, 0 minus 3k. So I don't know if you're seeing how we're going to get a vector out of this. That's going to be 15i minus 6j and then a minus 3k. So there is our vector, our new vector, the cross product vector. That's v cross w, and that's in ijk notation, which we could also write in maybe what's more familiar for us, component form. It would be 15, negative 6, 3. So either of these forms is fine. They're both accepted representations of a vector. Now, this new vector operation has some remarkable properties. This new vector operation has remarkable properties, and I may need to go to a new screen to show all these because I'd like you to see all of them on the same screen. So I'm going to go there. And so the first property, so these are properties of the cross product. Properties of the cross product. So the first one is that V crossed with W is perpendicular to both V and W. So, for example, let's take, we just found our 15, negative 6, negative 3. That was our cross product vector. That was V cross W, if you remember from the other screen. And if we dot that with V, which was 2, 3, 4, then we're going to see 15 times 2 is 30, negative 6 times 3 is a minus 18, negative 3 times 4 is a negative 12, and sure enough, that's equal to 0. So we can see that V cross W is perpendicular to V. And in a similar fashion, if we take our cross product vector, 15, negative 6, negative 3, and dot that with 105, that was our original vector W, then we're going to get 15 plus 0, and then minus 15, and sure enough, that's equal to 0, 2. So we can see that our cross product vector was perpendicular to both of the originals. Pretty amazing. Now, something that's kind of weird too, that V cross W, it is not what we would say commutative. That is, in just about every multiplication that we have learned so far, the order you multiply them in doesn't matter. 3 times 5 is 5 times 3. Well, not so with cross products. When you switch the order, you change the sign. You might remember that because when we switch the order, we're switching the order of row 2 and row 3. And so remember, when you switch the order of a row or a column in a determinant, it changes the sign. So it turns out that V cross W is the opposite, the negative of W cross V. Now, these follow, and I'm going to mention that here because we've talked about it. So this is called the right-hand rule for cross products. So, and this may challenge my ability to draw this, but the way you can tell what is going to happen with how the perpendicular vector looks is if you extend your right hand, so like you're going to shake somebody's hand, And so, yeah, I can't do that very well. So that's your right hand. So you're holding that out like you're going to shake somebody's hand. Now, if you bend your fingers so that with your hand it forms a right angle, and you let so right there, these are your fingers over here, so that's kind of sort of facing you. Your hand is still extended over here, like you're offering to shake somebody's hand, and you let your thumb come straight up there. Then this is how the thumb represents V crossed with W. That's the direction that cross product vector is going to be when V is your fingers and W is your hand. So when you're doing that cross product vector and you got your I, J, K, and we're doing V cross W, remember we're going to put V1, V2, V3 as that second row, and W1, W2, W3 as the third row. So when you do V cross W, then your thumb shows you the direction of the cross product vector. That is, it's going to point up. Now, if you take that right hand, and this is going to be even more challenging. Now, if you rotate that hand, so now it's the thumb is pointing down towards the ground, and you still have your hand part is there, and now you bend your fingers. This is very awkward. Don't hurt yourself. So there are your fingers, and your thumb is pointing down. Then this is what it's going to look like when you have W crossed with V. So again, what you want is the leading vector goes where your fingers are. Okay, and so that's how it's going to look there. And so the idea is when you go V cross W, that cross product vector is going to point up. And when you go then W cross V, then that's going to point down. So the perpendicular vector will go down. And again, that's indicating that change in sign there. Oh, this may be better done in person. Now we have that U crossed with the sum of two vectors, V plus W. You can, in fact, distribute that. So that is going to be U crossed with V, so remember that's going to be a new vector, plus U crossed with W. And so just to remember what we're getting here, V plus W is going to be a new vector. When you cross that with U, you're going to get a third vector, actually a fourth vector. And here you're going to get U cross V is going to be a new vector, and that was supposed to be a cross right there. And so U cross V is also a new vector, and when you add those, you're going to get a vector. So the result there is going to be a vector. Okay, so number 4, we can say V is parallel to W. V is parallel, so this is going to be a new way for checking for parallel. It's going to be parallel to vector W, if and only if, which we can abbreviate as IFF, V crossed with W is equal to the 0 vector. Okay, so we know that two vectors are perpendicular if their dot product is 0, and two vectors are parallel if they're multiples of each other, and if they're multiples of each other, then their cross product is going to be 0. So that gives you another way of recognizing that two vectors are parallel. Now this one's kind of crazy. The magnitude of that cross product vector. So you find this new vector V cross W, you find its magnitude. It turns out that is equal to the magnitude of V times the magnitude of W times the sine of theta, where theta is that angle between V and W, where theta is the angle between vector V and vector W. So geometrically, I'm going to give you a picture here in a moment. So geometrically, the magnitude of U cross V, or U cross W rather, is the area of the parallelogram formed by U and V. I keep saying U and V, U and W, or V and W. Sorry about that. So that was really V, because I started out with V's and W's. So here's an idea of what a picture looks like. So here's our vector V, and then we move it so that, you know, our vector W is going to share that same initial side. So now they form a parallelogram. And our cross product vector, and I didn't do this very well because it was going to show the right-hand rule. So if we follow our right-hand rule, where V is going to be where our fingers are, and crossed with W is going to be where our hand is, then when we squeeze those together, that's going to make that cross product vector go down, following the right-hand rule. So that is V cross W. So what we're saying by this property number 5 is that the magnitude, the length of that vector, is equal to the area of that parallelogram formed by vector V and vector W. Isn't that remarkable? Pretty amazing. So let's I'm going to go to a new panel here. And so we are going to use the cross product to find an equation of a plane. So use the cross product to find an equation of a plane. So I'm going to pause this and write this down so I don't spend so much time here. I'll be back momentarily. Okay, so here's our question, our first question, part A. Let's find a non-zero vector that's perpendicular to the plane containing the point P, Q, and R, and you can see the coordinates. So what we need is we can find a vector perpendicular to a plane. Remember, our go-to way of finding a perpendicular vector is going to be our cross product. So if we take two vectors that share the same initial point, so if we go PQ and PR, then, you know, visually we're going to have, you know, PQ is going to look like that, and then here's R that's in the same plane. So if we take their cross product, we're going to get a vector that is perpendicular to both of the original vectors, which is going to then be a vector perpendicular to the plane containing those vectors, which is the plane containing PQ and R. So PQ, we're going to go tip minus tail. So we go 2 minus the 1 is 1, and 5 minus 0 is 5, and 0 minus 3 is negative 3. So there's our vector PQ. Similarly, PR is going to be 3 minus 1 is 2, 1 minus 0 is 1, and 4 minus 3 is 1. So our vector perpendicular to those, to the plane even, I'm just going to call it, so our normal vector, that's an N, is going to be our PQ crossed with PR, which we are now learning is going to look like evaluating a 3 by 3 determinant, where we write the first row as IJK, and since we're starting with PQ, it's going to be in the second row, and then the 2, 1, 1 is going to be in the third row. And we're going to evaluate this using expansion by minors. So I times its minor is going to look like I times 5, negative 3, 1, 1. And remember, always we're going to expand along row 1, which is going to make that second term be a minus j. times its column, which times its minor rather, which is going to be 1, -3, 2, 1, and then a plus k times its minor, which is 1, 5, 2, 1. And so we're going to get for this normal vector to our plane, this vector that's perpendicular to the plane, we're going to get 5 minus a -3, 5 minus -3i, and then minus a 1 minus a -6j, and then a plus 1 minus 10k. So that's going to look like 8i, and then 1 plus 6 is 7, that's a minus 7j, and a -9k, or if you prefer, we can go back to our component form of a vector. Either one is going to be okay. And so there's our normal vector. That's our vector perpendicular to the plane. Now remember, that is our ABC for our equation of a plane. That's going to be in the form ax plus by plus cz equals d. And we can find this d by using any of the points in the plane for x, y, and z, and then our a, b, and c. So we've got 8, which is coming from our normal vector. And I'm gonna, do I like anyone better? I like point P because it's got that 0 in it, so I'm gonna use that. So 8 times 1, and then we have a minus 7 is our B, times 0 is the y coordinate of point P, and then a minus 9, that's our C, our z component of our normal vector, and then 3 is the z coordinate of P, and that's going to be our D. And so that's going to be 8 minus 27, I believe, is going to be our D. And so that's going to be D equals -19. So our equation of our plane is going to be 8x minus 7y minus 9z is equal to a -19. Kind of a slick way of coming up with an equation of this plane. So that is our, so I guess that was what it was going to be my part B, was get the equation of the plane. So I didn't even write that question, but our non-zero vector perpendicular to the plane, that was right here. So there's our answer to part A. There's our vector perpendicular to the plane. My second question was going to be to find an equation of the plane. That we just did there. And my third question is going to be, can we find the area? Can we find the area of the parallelogram with sides PQ and PR? We find the area of the parallelogram with sides PQ and PR. And so if you remember, what we said is that the area of that parallelogram is going to be the magnitude of our cross product vector, which we've also called n. And so that's going to be Pythagorean. So we're going to get the square root of 8 squared, which is 64, and -7 squared is 49, and the 9 squared is 81. Yikes. So that's going to be what? I have 113, 114, 214. Does that sound about right? No, I don't think I got that right. Let's see, 60 and 40 is 113, 114 and 80 is going to be, so I better write this out, 113 and 81 is going to be 194. Oh, struggling in the arithmetic department today. Okay, so there is our answer to that one. Okay, I'm going to go to a new, I think I'm going to stop this video and make a second one because this is getting kind of long.